We did not finish this one, I don't think, in the video. Yeah, you were supposed to try it on your own. Hopefully this is the same one that I gave you, because I can't remember offhand.
There was no half hour. Wait a second, if there were. Cross, this is really long.
I actually can do that.
Okay, now she's done. Miss Cross?
Good?
Question. Can you split up... Oh, it's great. When you split up that ln thing, do you have... Like, does the constant split with it, so you have two with each one?
Yep. Well, we're gonna go through this one together. So, this should be everybody following along with me here. You have a product. Yeah.
Okay, so like that 4x squared, if you were to separate that, could you actually make that 2x, like 2 ln 2x, because the 4 could be considered 2 squared?
You could.
Okay.
Okay. And starting again. We're going to split this up into two log terms. Shh. And I'm going to actually bring this 1/2 out in front, which would cancel out this 2, so I just have that. Oh dear, I'm going to run out of space again. Well, we'll just know that that's there as well. Okay, and then y prime. I think I'm set here to take the derivative of each part. We're going to go slowly here. It's the same thing. 3 log 4 squared. Alright. Derivative of this will be 1 over u times u prime. Or you can think of it as u prime over u. So my u prime is going to be 8x. That 2 is going to still be on the top there. Sorry, I know you can't see it, but there's a 2 right there. So it would be 16x over u. We'll do the simplifying in the next step, so don't worry. Same thing here. This is going to be u prime over u. There's u prime over u. This, the exponent, is a function of x, so this is the a to the u rule, which is ln of a.
Do we have to put parentheses around the whole thing because it's all being multiplied by a negative?
They're all going to be multiplied anyway. Let me do the...
Negatives, I don't understand. Like, you got the minus in front of it, so don't you have to, like, distribute that to everything?
Because all three of these things are being multiplied, it's implied that the negative is attached to all of them.
Oh.
You're not adding anything. Okay, so all of this is the derivative of that. Because you have ln of a times a to the u times u prime. The derivative of this, is there any of the log rules that I have to use here, or is this just the rules that we've used before?
It's just rules before.
Just rules. Yeah. So we're going to have minus 2 secant of 4x, because the outside function is the square. And then the derivative of the secant is secant tangent. And then you have to chain on the derivative of the inside function of 4x. So all of this is the derivative of that. And then the last part here would be taking the derivative of that log base 5. So that derivative rule is 1 over ln of a times u prime over u, where u is my argument here. So the 3 is going to be on the top over ln of a. It is 1 over ln of a, but the 3 is there, so it has to stay. And then multiplied by u prime over u. So u prime is going to be 8x over u, 4x squared. Now the only simplification that can really happen here is in this first term, you could reduce your numbers and reduce the x's. You can also do that here. And then the only other thing you could do is take that 4 that's chained onto the end of that term and move it to the front and combine it with a negative 2.
Can't you make it a CD squared though?
You could also do that. But I'm going to stop there so that you can see each part separate. But that problem pretty much made you use every rule that we've learned.
Multiply the 3 times the 8, so you get 24x over ln 5 times 4x squared.
Yes, you can. No. I wouldn't give you that many, though, in one problem.
But they might not.
They probably wouldn't give you that either.
Can you also reduce the x on the last term?
Yep.
Okay.
I'm just curious. People can do it. Are they looking for us to fail?
I'm pretty sure they are.
Like when they're making, are they sitting there?
And I'm looking for you to succeed, and part of that is practice right now. So, flip the page. Okay, these are the 4 types. For, I think it's just D2, but it might be D2 and D3. Is this somebody other standard sheet quickly that I can just grab or look at really quick? Yeah, sorry, this is D2 and D3. And we're going to do 2 examples. Okay, this is taking something like this. Make that a +1 on the bottom. Okay, now I know we've been working on log rules and exponential rules. Is this in any way a log function or an exponential function besides the exponent of 3 and 1/2?
I don't think so.
No.
That's a trick question.
Well, no, it's not a trick question.
Yeah.
The way it is right now, it's not. But if I was going to take the derivative of this, I would have to use what rule? The quotient rule. And then within the quotient rule, I would have to use the
Chain rule.
Chase, stop doing that, please.
Oh, sorry.
But sometimes they'll ask you to use something called log differentiation, which is basically using the properties of logs to make this simpler to take the derivative of. Okay, that's why it's a 4-type problem, because it's not essential that you know, but sometimes, very rarely, they've referenced it, so I do want to make sure we cover it. Now, this is an equation. One of the nice things about equations is you can do whatever you want to an equation. You just have to do it to both sides. Hold on. So what we're going to do here is we're going to take the ln of both sides. Ln is a function on an argument. So what we're going to do is we're going to, whoops, if I can write it correctly, take the ln of both sides. Now the reason this is going to be useful is that now we can employ the properties of logarithms to actually separate that quotient and break it apart into pieces. Brad?
If we did the quotient rule on like the test, we wouldn't get the 4 then.
Correct. Because the directions will clearly state use log differentiation to take the derivative of this. Okay. Chase?
Will you get the exact same answer though?
You won't. You'll get a more simplified answer doing it this way than you would if you did the quotient rule and the chain rule within the quotient rule. Okay. So, ln of y is going to stay ln of y over here. This is a quotient, so I'm going to break apart this quotient by using the properties of logs. That is going to be my first argument, but that 3 can come out in front, so I'm going to have that expression minus. That's to the 1/2, so I could break up that next one into that term. Okay, so powers come out in front, and then the quotient is no longer, because properties of exponents. Or properties of logs. I keep saying that. Okay. And then we take the derivative from left to right. Now, the derivative of ln of y is 1 over y times dy over dx. It's like we're taking it implicitly. So we have 1 over y times dy over dx. Then the derivative of this would be u prime over u, which would just be 3 over x minus 2, because the derivative of u is just 1. And over here, we'd have u prime over u, so you'd have 2x over 2 times x squared plus 1, because that 1/2, the 2 would have to be on the bottom still. But essentially, you could reduce the 2 and the 2.
Is that why you wrote it, like, with the 2 out in front, not them distributed in it, just right away?
Yeah. Okay. Now, if I wanted to get dy over dx by itself, what would I have to do here? Multiply both sides by y. But y is that original fraction, correct? So we could write y is this, and then times that. Okay, so this is y. Maybe you want to identify that as y.
Is it more simple than the quotient rule?
If they're asking you to do log differentiation, they are asking you to do that. It is simpler than doing the quotient rule and the chain rule within the quotient rule. Looks messier than that.
I have a question.
Yes, TJ?
Do they expect you to distribute?
No.
Wait, how did you get the last part?
How to get the last part?
Yeah,
Because I had that 1 over y. So to get dy over dx by itself, you have to multiply everything by y. But y is equal to that original fraction. So instead of writing y, I just wrote the original fraction of what y was equal to, so that everything's in terms of x. However, if you had to use this, let's say you had to find the equation of a tangent line and you were given a point, you could just multiply by y, because then you'd have the x value and the y value that you could just plug in.
Did you cancel out the 2?
And I canceled out the 2's, yep, to get that. Okay, let's look at another one.
It's gonna be log differentiation, right?
Yeah, both of these are log differentiation problems.
Okay.
Okay, so again we have a function where if you did the quotient rule, you'd have the chain rule and a product rule kind of all in there. So it'd be a big problem at the end of it. So only if the directions state use log differentiation, then that's what we're doing right now is log differentiation. Which to start it off, you just take the ln of both sides. So we're going to take the ln of both sides, and then use the properties of logs to break this apart into pieces. So you have ln of y. Now, if you remember from expanding log expressions in Algebra 2, we always broke up the division first and then broke up the multiplication. The first thing that you would do is have ln of sine squared x times 8x cubed minus 2 times ln of 4x squared minus 1. And then we could break that up one more time because there's two things being multiplied. So you'd have that. we can go through and take the derivative of each piece. So the derivative of ln of y is 1 over y times dy over dx. The derivative of that next term is going to be u prime over u. What's going to be u prime there? What's the derivative of sine? Cosine. So you'd have 2 cosine x over sine x, which we could make that a cotangent if you really wanted to. Then the next piece, u prime, would be 24x squared over 8x cubed. And then here we have u prime over u again, so you'd have 8x over, that would be 16, because you still have that 2 on the top. 16x over 4x squared minus 1. And then your last step would be to multiply everything by y, which y was that original fraction.
Or divided by a whole number though, right?
Yep.
On just like unit tests, would it be wrong if we just left it as y?
If you had a real long equation in the first place, you just keep going around.
If you drew an arrow or something, that would be sufficient. Like I would have to know that you knew like what could be plugged in for y if I did ask you to plug in for y. So if you took this and drew an arrow to the y, that's fine. Okay, so that's about as simplified as I would expect to see it, where the y has been changed back in terms of x. And then you have
A little bit of identity from there.
cosine over sine, you can reduce to be cotangent x. And the 24 over 8 can reduce to 3. And those can reduce to just an x on the bottom. Okay, we're going to try one of these on the whiteboard.